Good morning, good evening, good afternoon, and welcome back to another math lesson. Today we are going to be moving on to lesson number 3 of our transformations unit. We're talking about stretching and compressing graphs of functions. Okay, so let's get started. Stretches and compressions change the shape of the graph, but do not change the orientation of the graph. Okay, so a vertical stretch is represented by the form y is equal to a times f of x, where a is the vertical stretch factor. Okay, so this is what it's going to look like, where a is the vertical stretch factor. The phrase about the x-axis means that the graph will be stretched such that the center is the x-axis. It's the same idea as taking a stretchy cloth and then pulling it pulling with both hands in opposite directions. Okay, so that's what you can kind of see by the diagram located below. Okay, so we can actually see that, I mean, it's the same cloth. There's nothing that's being changed, only that it's being stretched. Okay, we haven't moved it left or right or up and down, right? The only thing that we've changed is that we've actually just stretched out this piece of cloth, or what we will be doing, stretching out graphs. Okay. So when we stretch out the point, we can note that the point xy becomes the point, okay? It now becomes x and then a times y. So this only affects your y's, okay? So if it's about the x-axis, it's only going to affect your y values, okay? So when a is greater than or equal to 1, there is a vertical stretch, okay? When a is when a is greater than 0 but less than 1, it's a vertical compression. So it's going to be squished, okay? And when a is less than 0, so that means there is a reflection on the x-axis as well as a stretch or compression. So in the previous lesson we talked about reflecting graphs about the x-axis and the y-axis. So if you can't quite remember how to do that, make sure you go back to the previous lesson video and go over the reflection about the x and y-axis, okay? But when a is less than 0, you have a reflection as well as a stretch or compression. Okay, which brings us to a few examples here. So graphs of the form y is equal to a times f of x, such as the first one. We have y is equal to 3 times f of x. This means that there is going to be a vertical stretch. Okay, so a vertical stretch by a factor of 3. So essentially what that means is you're going to multiply all of your y values by 3. Okay? The next one says y is equal to 2 times f of x. So that means there is going to be a vertical stretch. Okay, so this is going to be a vertical stretch by a factor of 2. So then this is going to be the same thing. Your x's remain the same, but you're going to multiply all your y values by 2. Which brings us to our next example, y equals f of x. Well, this is going to be your original function. Okay, so this is your original, or what's also called your parent graph. Okay, so everything remains the same. Okay, so this is your x values remain the same, and also your y values as well. Okay, so this is where your terminology is going to change a bit. So we have y is equal to 1/2 times f of x. So remember how you use your words, okay? So I'm going to say that this is going to be a vertical stretch, okay, by a factor of 1/2. So that means your mapping notation is going to be 1/2 times y. Okay, now I notice I say a vertical stretch. I have still stretched it, but it's of the factor of 1/2. Okay, so before we were talking about stretches and compressions. Okay, so if we were to say compression, we'll say compression the next one. So y is equal to 1/4 multiplied by f of x. So in this case, This is a vertical compression, okay, by a factor of 4. But with our mapping notation, it's still 1/4 times y. So you can say both. You can say stretch and compression, okay? Compression is used when you're given fractions, okay, for your a value. But then you switch back, when you say compression, you switch it back to a whole number, okay? Now, what I would recommend is that you just keep saying the word stretch, okay? That way you're always using the number that's given, okay? Especially for your y values in this case. So it means the exact same thing, right? A vertical compression by a factor of 4 is the exact same thing as saying a vertical stretch by a factor of 1/4. It means the exact same thing. It's just the terminologies you use. Make sure you don't mix the two up. So don't say a vertical compression by a factor of 1/4. That's incorrect. It's like a double negative when you were to speak, okay? So it kind of cancels each other out. So you don't want that to happen. So you either say a vertical compression by a factor of, and it's going to be a whole number, or it's a vertical stretch by a factor of the fraction. It means the same thing, okay? So make sure you understand the terminology of the two. Okay, moving on to the next part. So a horizontal stretch is represented by the form y is equal to f, and then in brackets b times x, where the reciprocal of b, so 1/b, is the horizontal stretch factor. So let's highlight some of this stuff here, where the reciprocal of b, okay, is the horizontal stretch factor. Okay, so that's an important note for us to have. Okay, so whereas with a was the horizontal stretch factor. Okay, you didn't have to change anything, but because we're in the brackets, we have to do the reciprocal of it to figure out what the horizontal stretch factor actually is. Okay, so the phrase about the y-axis means that the graph will be stretched horizontally, such that the center is going to be the y-axis. Okay, so an important note: when the horizontal stretch factor is given to you in a sentence, you can apply it to the graph without taking the reciprocal. Okay, you only use the reciprocal when reading the stretch factor from an equation. Okay, so that's when it comes into play. So when the horizontal stretch factor is given to you in a sentence, you can apply it to the graph without taking the reciprocal. You only use the reciprocal when reading the stretch factor from an equation, okay, such that y is equal to f times b of x. Okay. A note, so important. So let's actually scroll down so we can see what we're talking about. So note, point p, your point xy becomes the point. It's going to be x over b. So you're going to divide it by b. But your y's remain the same. So when b is greater than or equal to 1, that's a horizontal compression. Okay, so you're squishing it. Okay, when b is greater than 0 but less than 1, there is a horizontal stretch. And when b is less than 0, well, there's the reflection as well as a stretch or compression. So it's actually going to be the opposite of what a does. A basically tells you what's happening. Okay, a is very specific in saying if it's a whole number, you're going to stretch it. If it's a fraction, it'll be a compression. But b is opposite. So when b is greater than 1, it's actually a compression. Okay, when b is in between 0 and 1, that's when you have a stretch. Okay, and then when b is less than 0, well, you have a reflection, and then you have a stretch or compression. Okay, let's try some examples of what I'm talking about here. So we have graphs of the form y is equal to b, or f of b times x, such as we have y is equal to 4. Okay, so y is equal to f of 4x. So that's going to be a horizontal. And now it's, again, with the wording, you have to be very careful. Okay, so this is a horizontal stretch by a factor of 1/4. That's the reciprocal, right? We said earlier that the stretch factor is the reciprocal of b. So that's why we said this is a stretch by a factor of 4. Okay? You could also say it's a compression by a factor of 4. Okay? So either a horizontal stretch by a factor of 1/4, which is the reciprocal of b, or you can say it's a horizontal compression by a factor of 4. It means the same thing. So if we're looking at the mapping notation, well, that's going to be x/4 and y remains the same. Okay, so that's where we have the reciprocal of it. Okay, the next one, y is equal to f of 2 of x. Well, that's going to be a horizontal stretch. Okay, so that's a horizontal stretch by a factor of 1/2. So this is, again, the reciprocal. So it's going to be, for a mapping notation, it's going to be x/2. Okay, and then y. The next one, y is equal to f of x. Well, that is the original, okay, the original or parent function or parent graph. So everything remains the same. So it's still, for your mapping notation, it's still x and y. Okay, so it still remains the same. The next one we have is y is equal to f, and then we have a half. Okay, so this one is going to be a horizontal stretch. Okay, so this is going to be a horizontal stretch by a factor of 2. Because we have taken the reciprocal of 1/2. And then again, the reciprocal of 1/2 is going to be 2. So that means it's going to be 2 times x and leave y alone. Okay. Next one we have, and finally, oh, sorry, the next one is the last one we have. Y is equal to f of 1/4 x. Again, this is going to be a horizontal stretch. Okay, so a horizontal stretch by a factor of 4. Again, I've taken the reciprocal of b. So again, it's going to be 4x, and then y remains the same. Okay? So again, that's the difference between your a value and your b value. Your a value is going to remain the same. Okay? You don't change it. Okay? Whereas your b value, in order to state what the stretch factor is, you have to take the reciprocal of it. And when you're using the mapping notation, you have to take the reciprocal of b. Okay? Let's try some examples, and hopefully this will become more clear. Okay, example number 1. Draw the graph resulting from each transformation. We have y is equal to 2 times f of x. Okay, so this is for part A. So what we're going to do is let's do the mapping notation first. And essentially, what's happening? Okay, so we can say that this is going to be a vertical stretch by a factor of 2. We're basically stretching out all the y values. Okay, so if we're going to map out the pairs x, y, and then do the mapping notation to it, we are going to multiply all the y values by 2. So for your original points of x and y, we'll do this really quick. Okay, so that's your points are going to be this. Okay, so those are the points from the original function. What we're going to do now is we're going to stretch all those values, all those y values by 2. So our x's will remain the same. So it's going to be -4, -2, 2, and 4. So those all remain the same. But we're going to multiply all the y values by 2. So now instead of it being at -4, it's going to be at -8, -4, -4 again, and then +4. Okay, so let's see how this actually looks. Okay, so this first one, -4, -8. Okay, so it's gonna be stretched all the way down to here, and then the -4, the -2, -4. Okay, so it looks like it stretches to now become here. Okay, this value will also remain the same, but then this value will stretch up here. 1, 2. Okay, so this is what it has now been stretched to. So we can go ahead and we can connect all the points. Like so. there. Okay, and because of that, that's now what the new graph will look like. I'm just going to draw on the points again so we can see where they were. Okay, but that is how your vertically stretched graph will look. Everything's been just stretched vertically. Okay, nothing's been stretched horizontally, nothing's been moved horizontally. It's only vertically in this case. Okay, but that's what this graph will look like. Moving on to part B, we have part B is y is equal to 1/2 of f of x. So this is going to be again, a vertical stretch by a factor of 1/2. Okay, so that's what it's now turned into. So this is the exact same graph as before, so we can go ahead and we can fill in the parent function for x and y. Okay, so now that we've gone ahead and done that, let's now apply the mapping notation to it. Okay, so we're going to say our x's remain the same, but we are going to multiply all the y values, or essentially divide all the y values by 2. Okay, multiplying it by 1/2 and dividing by 2 means the exact same thing. Okay, so if we divide all the y values by 2, it should give us the same thing. So we have -4, and then -4 divided by 2, well, that gives us -2. Our x value remains the same at -2, but our y value, okay, so -2 divided by 2 gives us -1. 2 remains the same, but we get -1. And then finally 4, but then we have 1. So let's go ahead and let's map out these points. Okay, so now that we've gone ahead and mapped out these points, let's go ahead and let's graph it. And there you go. Okay, so that's how it's graphed. I'm going to add in the dots so that we can see a little bit better. Okay, and there you go. That is the exact same graph, but it's been vertically stretched by a factor of 1/2. Okay, so you can think of it as it's being compressed. Okay, it's been compressed by a factor of 2. Okay, or vertically stretched by 1/2. Means the exact same thing. Okay, but essentially it's been taken and it's just kind of been squished. Okay, but that's how you would do these two examples. Moving on to the next two examples, we have y for part C, y is equal to f of 2 of x. Okay, so in this one we have a horizontal stretch by a factor of 1/2. So we have taken the reciprocal of the b value. Okay, so essentially, again, these are the exact same points as before. Okay, but now what we're going to do is we are going to basically divide all the x values by 2. Okay, so let's go ahead and let's put our mapping notation in, and then we'll go ahead and we'll graph. So again, it's going to be x/2, but our y's are going to remain the same. Okay, so it's going to look like, I'm just going to move it over here. Okay, it's going to look like this. Okay, so it's going to be, instead of it being at -4, -4, it's going to be now at -2, -4. Okay, instead of it being at -2 and 2, it's going to be now at -1 and -2. Instead of it being at 2 and -2, it's going to be at 1 and -2. And then finally, the last one was at 4 and 2, but we're going to divide that by 2, so it's going to be at 2 and 2. Okay, so those are our new points. So let's go ahead and let's plot those out. Okay, so we have gone ahead and we've plotted out these points. Okay, so let's go ahead and let's graph this. So it's going to look like this. Notice how our y values remain the same, but our x values are the ones that have changed. I'm just going to add in these points as well so we can see where our points are. Okay, so there is a horizontal stretch by a factor of 1/2. Okay, but it kind of looks like it's been compressed. It's true, it has been compressed, but the compression factor would be 2. Okay, the horizontal stretch factor is 1/2. That's where the reciprocal of b comes in. Okay, moving on to the last example we have, it's y is equal to f of 1/2 of x. Okay, so this is going to be a horizontal stretch by a factor of 2 because we have taken the reciprocal of b. Okay, so our mapping notation is going to look like 2 times x and then y. So our values are going to change. So instead of it being at -4 and 4, it's going to be at -8 and -4. Okay, so we're just going to double all of our x values. Okay, so the next one will be at -4, -2. And the one after that will be, well, that's at 4 and -2. And then the last one's going to be at 8 and 2. Okay, so let's go ahead and let's plot these points out. Okay, we've gone ahead and now plotted these points out, as you can see. What we'll do now is we'll actually connect the dots. Okay, so it's going to look like this. It's going to look like it's been stretched. Okay, and it's been stretched about the y-axis. Okay, so it's stretched horizontally. Okay, let's add in these points so you can actually see where our new function, our new points are. But essentially, that's it. Okay, that's now been horizontally stretched by a factor of 2. So we've done now both the vertical stretch, okay, and a horizontal stretch, and you can now see the difference between the two. Okay, but that is it for today's lesson on horizontal and vertical stretches. I hope you enjoyed it. Okay, and remember, when it comes to math, keep calm and show your work.